In the previous video, I showed you how to solve problems in Hückel theory by finding the eigenvalues of the matrix which we derived in the first video. In this video, we're going to find the wave functions and thus diagonalize the matrix using symmetry. As our example, we're not going to look at hydrocarbons, we're going to look at H3+ and the sigma framework. The question is, does H3+ take a triangular form like this or a linear form? And I'm going to show you two ways. The triangular form I'm going to analyze using a formal way, and for the linear case I'll use the intuitive way. What we'll need is the character table for C3V. C3V, because the triangular H3 has the identity, which means it just doesn't change. It has a C3 axis in the center here, and you can either rotate this way, which gives you C3+, or you can rotate this way, which we call C3-. So there are two C3 axes in the Z direction, which is coming out here. We also have three mirror planes that are vertical with respect to this the central axis, the C3 axis. These mirror planes go through each of the hydrogens. There's one here, and one here, which we're going to call sigma V1 because it goes to the hydrogen I labeled 1, sigma V2 because it goes through hydrogen 2, and sigma V3 because it goes through H3. Now, I'm kind of assuming you know a bit group theory already, but I'll walk through it quite slowly. So, what we want to do is we want to find wave functions that respect the symmetry of the molecule here. And we'll do this by applying our symmetry operations and seeing how our orbitals, which lie on the H centers, so we might as well say how our H's move as we apply the symmetry operations. So the character of our overall molecule looks as follows. If we apply the identity, each of the hydrogens will stay in its place. So 3 out of 3 stay in place. So we give it a 3. If we apply C3, so we rotate around here 120 degrees in either direction, we see that each of the hydrogens will move. So we give it a 0. When we apply our mirror plane, the mirror plane goes through one hydrogen each time, which means if we mirror, for example, across here, hydrogen 1 will stay where it is, hydrogen 2 and 3 will swap places, so we give it a 1. Now, this representation of our H3 molecule now needs to be split into its irreducible representations, which we can see here. So essentially, what we're trying to do, we're trying to generate 301 out of the numbers we're seeing here. And there are two ways of doing this. If you get a bit more experienced, you can just read it off. And if we do that, we see 1 plus 2 is 3. The only way to get a 0 in the middle is if we take a 1 and a -1, or a 1 and the -1. And then the only way to get to +1 in the last line is if we take A1 and E. So thereby we can say for sure that this is just A1 and E. Alternatively, we could have used the reduction formula, which looks as follows. I'll just give you one example. So we say the number of A1 irreducible representations, which I call irreps, is 1 over the group number, which is 6. Why is it 6? Because we have one identity, 2 C3 axes, and 3 mirror planes. So 1 plus 2 plus 3 is 6. And then what we do is we say the character of our representation is 3, and we times 3 times 1, because we're looking at A1, and the character for the identity of the irrep A1 is 1, so 3 times 1, and then we just have 1 times the identity. And then we add 0 times 1 times 2. And we add 1 times 1 times 3, which comes out as 1. That means we have 1 time the irrep A1 in our representation, which is what we just showed by observation anyway. Okay, having done that, we know that the representation of a H3 molecule can be broken down into an A1 and an E symmetry type wave function. But now we want to see how exactly our wave function looks. Formally, we would have to apply the projection formula. In order to do so, we need to see where each individual orbital or H atom moves when we apply each of the operations. That means we need to split C3 plus and C3 minus. So what I do, I'll write in the table each of the operations, sigma V1, sigma V2, and sigma V3, and here I'll write H1, H2, and H3. And now we need to go through each of the operations and see what happens to, for example, H1. If we apply the identity, nothing changes, so H1, H2, and H3 stay how they are. If I apply C3 plus, I see that H1, if I rotate this way, becomes H2, H2 becomes H3, and H3 becomes H1. For C3 minus, H1 becomes H3, H3 becomes H2, and H3 becomes H1. Sorry, H2 becomes H1, and H3 becomes H2. If I apply sigma V1, I see that H1 stays how it is, and the same is for sigma V2 for H2, and for sigma V3 and H3. And what happens as well is when I apply sigma V1, H2 and H3 swap places, so H3, H2. If I apply sigma V2, H1 and H3 swap places, and here H2 and H1 swap places. Now, having done this, I apply the projection operator, which, if I look at A1, my wave function for A1, considering H1 first, is the character of the irrep we're looking at, which is A1, times the place where our hydrogen moves when we apply this operation. So it's 1 times H1, because there's a 1 here and H1 here. Then plus, again, the character of A1 is 1, and under C3 plus it moves to H2, so 1 times H2, plus 1 times h3 plus 1 times h1, 1 times h3, 1 times h2. So, and now I would have to do the same with h2 and h3, but as we can quickly see, is because the character of a1 is plus 1 everywhere, they're going to look exactly like this wave function, which means we've already found our wave function that transforms as the a1 irrep. And if I normalize it, it will look like this. h1 plus h2 plus h3. And now I normalize it, which gives it a factor of 1 over root 3. And we see that the a1 irrep consists of all our hydrogens having the same phase. That's why they're all plus. Now, I need to do the same thing for the E irrep. So, psi E H1. And now, my character of the E irrep for the identity is 2. So I have 2 times H1. And then I have minus 1 for each of the C3 operations. So minus H2 minus H3. And there's a 0 for the mirror planes, so I can just ignore these. If I do the same now for H2 and H3, I will find that I get 2H2 minus H1 minus H3 and 2H3 minus H1 minus H2. So I get 3 wave functions that transform as the E irrep. But the problem is, these 3 wave functions are not orthogonal, and I have one too many because the E irrep is twice degenerate, not 3 times degenerate. So what I do, I take 2 of these to generate an orthogonal wave function that's orthogonal to the first of them. Here it's arbitrary which 2 I choose to be orthogonal to the third one. I take these ones and I'm going to subtract them so that I get the wave function that looks as follows. I get 3H2 minus 3H3. As I can see, the H1s, they cancel if I subtract the 2 wave functions. And from here, I have the wave function being 2H1 minus H2 minus H3. Again, I need to normalize them, which gives me a factor of 1 over root 6 here, and a factor of 1 over root 2 here. Again, this is just for normalization. So now, I have all the wave functions, and if I were to draw them, A1 looks like this, all of them being in phase. The first E wave function looks like this, a large coefficient at the top, and 2 small coefficients at the bottom. And this one looks like this, 2 small coefficients out of phase, and nothing for the third position. This is how our wave functions look like. So now, if I solve the determinant, generally speaking, the matrix elements look like this. Wave function of example A1, H, A1, and then here on the diagonal, it's always the same left and right. Wave function E1, H, E1, and E2, H, E2. So what about the off-diagonal terms? I just said that we have chosen our wave functions in E to be orthogonal, and the A1 wave function by default will be orthogonal to the E wave functions. So for example, I look at this matrix element right here, I would find E2, H, A1, which is just 0. And so with what we did here, with finding the wave functions like we did, all the off-diagonal terms will be 0, and we directly have our diagonalized determinant. Now, if I solve the actual matrix elements, how do I go about it? I look at, for example, this wave function here, and I pick out one of the orbitals. So I pick out this orbital, and I check how many interactions does this orbital have. In this case, it has 1, 2 good interactions. Good, because they're in phase. So here I can write down alpha plus 2 beta minus E. Alpha, because this orbital will always overlap with itself, and the 2 betas for the 2 good interactions. Here, for the E-wave functions, this one looks a bit daunting because of the big coefficient on this one. But since the E-wave functions are degenerate, we can just look at the simpler one, at this one, and just evaluate the energy, and it will be the same for this entry and this entry. So if we look at this one and we pick out this orbital, it will have one interaction, since this is empty, and it will be a bad interaction. So we know that for the E-wave functions we get alpha minus beta minus E for both of them. And the rest is 0. So if we do this, we have a diagonal matrix from which we can just read off the eigenvalues, which are E1 is alpha plus 2 beta, E2 and E3 are just alpha minus beta. That's the advantage of using the symmetry approach. We directly get a diagonalized matrix which we can read off. So if I now draw an energy diagram, we have one level at the bottom and 2 levels above it. The one at the bottom is at alpha plus 2 beta, and the one above at alpha minus beta. And in H3 plus, we have 2 electrons to fill, so I fill them on the lowest level. And I see my overall energy is alpha plus 2 beta, and that twice, because we have 2 electrons in the orbital with the energy alpha plus 2 beta, which is 2 alpha plus 4 beta. Okay, so much for the formal way. Next, I'm going to show you the intuitive way, or the informal way, which builds on, well, intuition. And for the informal way, we're going to look at the linear version of the molecule. And we're going to say that this linear version can be built up of this plus this. So I'm going to look at the exterior hydrogens and their symmetry, and then I'm just going to insert in the middle hydrogen and see what happens. And for the exterior ones, since it's just two orbitals, they can either be in phase like here, or they could be out of phase like this. So these are two options. We either have them to be out of phase or in phase. And we can easily find the wave functions, which I'm going to call psi1 for the in phase one, which is just 1 over root 2 if I normalize it, and then h1, if I call this h1, h2, and h3, h1 plus h3. Psi2, I'm just going to say, is the lone orbital here. So psi2 is just h2, and psi3 will be the outer phase one, so 1 over root 2 h1 minus h3. So now what I can do, if I write on my determinant again, I get matrix elements similar to here, so that on the diagonal we'll just have all of these wave functions overlapping with themselves, which, since it's normalized, will always just give alpha minus e. For example, if I were to explicitly write out the first matrix element of psi1 with pi1, I would get 2 alpha, 1 alpha for the h1, 1 alpha for the h3, but since it's normalized, I just get a singular alpha. And then let's look at psi3. Psi3 is the out of phase combination. The out of phase combination can't overlap with psi2, because if I were to put this orbital in here, we would have one good and one bad interaction, so no interaction overall, so that I can write zeros in terms of overlap for all the interactions with psi3. Why do I say, by the way, that this orbital and this orbital don't overlap? Why do they not get a beta? The reason they don't get a beta is that they are too far away. Since I'm ignoring the h2 in the middle when I'm considering this long line, I'm not considering the actual, they're not actually bond like this to each other, so they don't get a beta. Now, what happens if I put h2 or psi2 into psi1? I see I get overlap on both sides. And how many times do I get a good overlap? Twice. So I expect to have 2 beta. But since this wave function has a factor of 1 over root 2 in front, I need to consider this, and so instead of 2 beta, I get 2 over root 2 beta, which is the same as root 2 beta. So again, if I solve the matrix element, which looks like this, for psi1 and psi2, I have overlap between h2 and h1 and h2 and h3, which would give me 2 beta. But because of this normalization constant here, I get just root 2 beta overall. Okay. Now, this determinant isn't quite diagonalized yet, but it's usually simplified. Because of the zeros over here, we can immediately expand across here, which gives alpha minus e, and then the 2 by 2 determinant, which we can now immediately expand in the usual way to give us alpha minus e, and then alpha minus e squared minus root 2 beta squared. And all of this is equal to 0. So from here, we can immediately read off a solution as the energy just being alpha. Here, we'll have to think about it a bit, but it's not that difficult because it says that alpha minus e squared is equal to root 2 beta squared. We just take the root on both sides and solve for the energy, and we get E is alpha plus minus root 2 beta. So now we found all three solutions. We found solution 1, which is alpha plus root 2 beta, solution 2, which is just alpha, and solution 3, which is alpha minus root 2 beta. Again, if I draw the energy diagram, it will now look like this. And this is alpha, alpha plus root 2 beta, alpha minus root 2 beta. And I have 2 electrons, I fill them in, I fill the lowest level. And now if I calculate the overall energy, I will get 2 alpha plus 2 root 2 beta. Again, the factor of 2 comes from the fact that we have 2 electrons in the lowest orbital. Now, if I compare this energy for linear with this energy for triangular, I can tell immediately that for H3+, the triangular form is lower in energy, hence H3+ will be triangular. What if I considered H3-? How would this change? So H3- has 4 electrons. So I would fill these orbitals here or put one in each here. Since this orbital in the linear case is non-bonding and these orbitals in the triangular case are anti-bonding, what will happen is that for H3- the linear form will be more stable than the triangular form. This way we can use our results to predict the shape of certain molecules and see how the electron count influences this shape. I also want to come back to an example from the last video, which was cyclobutadiene, which looks like this. Once you do a few of these symmetry analyses, you can get an intuition for the problem. So the lowest energy configuration will always be having all orbitals in phase so that we have 0 nodes. Then if we think about it, how do we get one less favorable, so to say? And the obvious answer would be to say, what if we have 1 node? Now, instead of all the orbitals overlapping, we just have 2 pairs of orbitals overlapping and repelling each other this way. But at the same time, I could have drawn my node here and have these 2 overlap and these 2 not overlap. These 2 not overlap. And then finally, I can also draw up a form where I have 2 nodes so that none of the orbitals overlap. Right? And if I were to draw an energy diagram, it would look like this. Since here all the orbitals overlap, so we're lowest in energy, here we have 1 node and 2 versions of 1 node, so they're degenerate, and we have 1 orbital with 2 nodes. Now, if we want to find the energy of all these wave functions we just drew up, we need to write them down explicitly. For the first one, we have all of them in phase and a normalization constant of 1/2. I'll just write 1 plus 2 plus 3 plus 4 now if I call my carbons 1, 2, 3, and 4. For one node, I will have psi 2 is 1 over 2, and then 1 and 2 are in phase, so 1 plus 2, but these two, 3 and 4, are out of phase, so -3, -4, and psi 3 is 1 over 2, again normalized. 1 and 3 are 1 and 4 are in phase, so 1 plus 4, but 2 and 3 are out of phase, so we get this. And finally, psi 4 has all of them alternating, so 1 over 2, 1 minus 2 plus 3 minus 4. Again, if I want the energies, I put them into the matrix. And now what I can just do is, again, I pick out one orbital. I see this orbital has 2 interactions because it's bonded to 2 others. And they're good interactions since we overlap, so I write down alpha plus 2 beta minus E. For psi 2, I again pick out one orbital. I see it has 1 good and 1 bad interaction, so no interaction overall, so it just gets alpha minus E. Psi 3 is degenerate with psi 2, and so it will also get an alpha minus E. And finally, psi 4 has 2 bad interactions, so it gets an alpha minus 2 beta minus E. And again, all the wave functions are orthogonal, which means I have a fully diagonalized matrix, which I can read off the eigenvalues from immediately. I read A1 is alpha plus 2 beta, E2 and 3 are just alpha, and E4 is alpha minus 2 beta, which I can put on the energy diagram. Alpha plus 2 beta, alpha, alpha minus 2 beta. I fill in the electrons, and this diagram should seem familiar from the last video. We see that this intuitive symmetry approach gives us the same solution as the mathematical approach from the last video, but this is all the space I needed. If you can manage to break down the system into an appropriate symmetry, you can get to solve your problem much faster and more efficient than you could otherwise. This is not always as simple as in these cyclic conjugated carbon systems, so that sometimes instead of using the intuitive approach, you will have to use the formal approach. But for larger systems, the formal approach will still be more efficient than just brute forcing the determinant. I hope these 3 videos helped you understand Hückel theory a bit better, and if you liked the videos and learned something, please leave a like and subscribe if you want.